Okay, hold on just a second. Well, I'm gonna kind of talk to fill some space while I'm trying to get this ready. Are there any questions people have generally about how the course is running, what's going on, having any trouble with assignments or anything?
The quiz was so hard.
But you're able to get in and
yeah, I
function
tend to really in the quizzes the average up. My quiz was hard.
Okay, good. Then I'm doing my job.
The lab quiz has to be done by Sunday?
Lab quizzes have to be done before the next lab. So yeah,
So, yeah.
those will be. And there's nothing dependent on it. So if you don't get it done by midnight on Sunday, it's not going to be a big deal. Okay. Did everybody get the emailed announcement about the presentation that's in here? Okay.
You told us about it as well.
Yesterday, oh, that's right, because I saw you guys yesterday, so that's no big deal. Okay. So especially since I told you all yesterday, you all looked at it last night. So you're already.
Nice long video.
Yes. Let me just run through this. I'm actually kind of seeing if I can do this without calling names out. And I think I'm going to make it. Wait. Oh, there it is. All right. Oh, it's with this week's material, so. Okay, so I just have this up on the screen because I wanted to remind everybody and point out this. The material for next week, if you go into this folder, is not there. There's not a presentation there. I am going to hopefully get that ready tomorrow. Normally what would have happened in average semester is that you guys would have either a Monday or a Wednesday lab, and the dean decided that you could all, well, there weren't enough people in the Wednesday lab group as they signed up originally to keep the class open, so everybody who's in there was offered to move to the Monday group, which most of those people did. But that means that I don't have anything at all on Wednesday mornings. So I'll be hopefully getting next week's presentation ready then. I might have to do it over the weekend, which is going to be really weird because I'm actually going to a conference over the weekend. So I'm going to bring a laptop and work on it in the hotel room if I can. But so I should have that stuff ready tomorrow, and if not, it'll be over the weekend, but then you'll have something to prepare for next week's class. And probably, if I do get it up over the weekend, besides sending out an email through the Blackboard announcement system, I'll probably also remind you of it on Monday on Lab. But, so that's the plan, at least. So, since all of you watched that presentation, I am going to be able to easily assume that you're comfortable with some of the basic ideas behind chemistry. And so what I want to do today is actually give you a chance to give you a chance to get to know some stuff a little bit better. That's kind of what we're going to do today and Thursday, kind of work with some of the important aspects of the chemistry that affect this course, and hopefully get everybody to understand a little bit better. So I'm going to start by giving everybody temporarily, you're going to give these back in class, one of these to look at. And what I'd like you to do is, I'm going to not talk for a while, which will make the recording part really kind of boring. But I want you to look at these and figure out what you're looking at, and which hopefully will be a pretty easy thing to do. But then also see what you can figure out about this and what it demonstrates. And in doing that, you're going to have to interact with each other. So feel free to get up and move around the room and talk to each other and that sort of thing, and figure out what these are about and what you learn from them. So I'll give you some time to do that. Go ahead. Move, make noise.
Sure, let's see this. You mean like a water molecule?
I think that's
I'm thinking like these two sides. They're not the colors.
Shares, right?
Neutron there.
Electrons.
Cheers.
Share with another.
So, yeah. Do they stick together?
I think so.
I was
Isn't it more, they don't stick to the white. So electrons.
Well, obviously, I'm just saying like.
Probably the simplest thing.
I know.
I wish I could get pictures.
I know.
It could be anything.
That's what we talked about. Because the water molecules, they
That looks like it. I don't. Are you guys sure? I'll try.
I know,
Oh, no, I
hesitation.
should have told my.
I know I can't draw pictures, I just wrote.
Okay, so I think people have gotten the chance to talk about this because I've heard, like, we've talked about, doing in the future. And kind of thing. So what is this that you're looking at?
The water.
What makes you think that it's water? How does that tell you anything about water?
Because there's only room for 2 other molecules to attach, so.
Well, there's room for 4 of the things attached to it. Every flat space is an attachment point. There's 2 on the big red thing and 1 on each white thing. But as far as the shape's concerned, this could just as easily be hydrogen sulfide. How do you know this isn't hydrogen sulfide? This is, I actually don't expect anybody to actually know how to answer that question. The reason you know this is water is because the big thing, the big singular thing is red and the 2 smaller things are white. If this were hydrogen sulfide, then the big red thing would be a big yellow thing. The color coding is actually very formalized in the process, so you know it that way. The geometry of this, the shape, is actually very important. The angle that the 2 hydrogens are attached to oxygen is very specific. It's 102 degrees. That's just a fact of how this molecule works. The reason for that is that oxygen can make 2 bonds to complete its valence shell. And so, and when you think about valence shells, you always think of pairs of electrons. So at the bonds, there are 2 paired electrons in those where it's connected to hydrogen. But then there are 2 unpaired, no, that's not how you say it, 2, I can't remember the word they use, but there are 2 more pairs around the oxygen. So drawing it in 2 dimensions, it would look something like this. So you have the oxygens and the hydrogen and the hydrogen. There's pairs of electrons represented by the lines for the bonds, but then the oxygen also has 2 more pairs of electrons that are just part of its normal electron shell. And the angle that these bonds occur at has to do with the fact that all of the other side of the oxygen needs to fit in those other electron pairs. So the shape and color actually are why you know that this is water. Now, probably really the reason why you knew this is water and not hydrogen sulfide is because why would we be talking about hydrogen sulfide in a physiology class? It's just not a very relevant molecule. That's a valid point to make too. Somebody said water is more important than hydrogen sulfide. I would have taken that and then I would have explained everything else, but that would have been a valid answer. Now, what did you learn about these models? What are they very good at demonstrating? How do they? Yeah, so they stick together. Okay. So, John, right?
Yeah.
Yeah. You were saying that there were, well, you said 2 connections, and I corrected you to say 4. But what it is that each of these flat spots, the 2 on the oxygen side and 1 on each hydrogen, has a rare earth magnet in it. It's a fairly strong magnet in it. And so you can connect things together just through magnetic attractions. Hopefully you realize something very important about how things actually stick together, which you actually kind of said it. So what's the point of how they stick together? What can and cannot happen?
Electrons can't stick to electrons, but they can to oxygen
I wouldn't say it like that.
or hydrogen.
talk about it in just physically what you were doing with them. What were you able to do?
Light colors can't attach to each other.
Right, so originally you said the white sticks to the red. So yeah, those will stick together, but if you try to push the red to the red, you feel the resistance. Does anybody know why actually you feel that resistance? You try to, right, and why will magnets resist each other like that?
Because they're polar.
Like charges.
Yeah, the polar, it's not charged, it's magnetic field. But yeah, that's the idea. What it's modeling for us is how charges interact, but it's really a magnet thing. But they're polar. There's a north and a south pole of every magnet. And so if you try to push the north poles of two magnets together, you'll get that kind of resistance. If you put the north pole of one magnet and the south pole of another magnet together, they'll stick. They have to be arranged that way. That's how magnets work. And the magnetism thing isn't terribly important, but what we're doing is we're using it to model how positive and negative charges interact. Okay? We can't actually put positive and negative charges in here because then people can get shocked all the time. So the magnets model the idea, but the white and the red stick together, the hydrogen and the oxygen stick directly together because one is partially positive and one is partially negative, which is red.
The right positive.
Right?
Isn't hydrogen, is hydrogen positive?
Hydrogen positive. I don't know which
I was
one's
talking
right.
about something else.
Yeah, because if you're saying the right's positive and then they just switch hands, like right and left doesn't make much sense there. So I don't know. But yes, it's the hydrogen that's partially positive. When oxygen and hydrogen make this bond that I've drawn here, you have the oxygen in the middle. It's got 2 electrons in its first shell, and then it's got 6 electrons in its next shell. The way I've drawn it on purpose is I put a pair of electrons there and a pair of electrons there, which are basically these 2 that we see there. And then these single ones are going to make bonds with hydrogen. And hydrogen already has 1 electron in its valence shell. And when it's the first shell, it only needs 2 electrons to be full. So now we have oxygen with picking up 2 electrons. Oh, I should have drawn them there. I should draw them there. Picking up 2 electrons, 1 from each hydrogen, so that it has 8 in its valence shell. And then hydrogen picks up 1 from oxygen, giving it 2, which is what fills its valence shell. But the electrons are not shared equally between the 2 atoms. It's enough for hydrogen to be sharing electrons and have a pair that it gets at least some of the time. That'll complete its valence shell. But those electrons actually spend more time around oxygen. And likewise for this one. So since the electrons are around oxygen more, that means that oxygen is going to be partially negative, and hydrogen, not having the electrons as much, will be partially positive. Okay. And so when we see water molecules coming close together, the partial positive charge and the partial negative charge will interact, just like any basic ionic bond, the difference being just that it's partial charges and not full charges, so that it's not quite as strong an attraction. But the models that you're looking at, these little water models, come with a kit that I get from this outfit. It's associated with the University of Milwaukee. And they sell a thing of 12 water molecules, and it always comes with these 2 pieces here. The big green one is representing a chloride ion, and the little blue one is representing a sodium ion, which would be sodium chloride. And so there's magnets on these also, and when I put them together, This is sodium chloride. This is a single salt molecule, although it's an ionic bond, so molecule is not the best term for it. Kind of looks like the new droid from Star Wars, but anybody? Okay, I'm just here. Anyways, so they're attracted that way also. You can have water molecules attracted to each other, like we've seen here, but also you can have sodium attached to water molecules, like such. Actually, let me grab some more waters. There are represented, and I don't exactly understand the chemical or physical aspects of these things to say why it's like this, but it's always depicted that 6 water molecules will surround an ion like this. And I truthfully don't really know why. Okay, we can do the same thing with, I mean, I understand that it's about attraction, but I don't know why it's not 6, 8, right? Oh, 6 definitely does. I just don't know why they are always represented like this. So anyways, here we have a sodium ion completely covered in water because the positive sodium ion is attracted to the negative, partial negative charge that's in oxygen when it's part of a water molecule. And here I have chloride completely surrounded by water because the partial positive charge in the hydrogen is attracted to the negatively charged chloride ion. If you put table salt in water, when it's dry, table salt, sodium chloride, crystallizes, but then as soon as you introduce it to the water, it dissolves because all of the water molecules that can be attracted to one or the other ion separates the ions apart and they dissolve in there. Okay. If I had enough water molecules, I could make a little, representation of salt water and have a bunch of these, what do we call these things again? Ions surrounded by water like that. And the ions can't come back together to make an ionic bond again because there's just too much water in the way. But that's what dissolving looks like. Now, what do we call the attractions between water molecules, like we're modeling with these things, or water to other substances like sodium and chloride? What are those attractions called? Bond is a general term, and so I'm asking specifically, which bond are we talking about when water is attracted to itself or things are attracted to?
Covalent bonds.
No. Hydrogen bonds, right? Weak attractive forces. Covalent bonds are very strong attractions because of sharing electrons. Okay, you have to expend a good bit of energy to pull two things apart like that. It's possible, it just requires a bit of energy. Hydrogen bonds are weaker attractions, and while it requires energy to break them, it doesn't require as much energy. Okay. So one way to break hydrogen bonds apart is with temperature. So if this was salt water and I heated it up, the energy of the heat would make these water molecules move around quite a bit more, and they'd eventually be separated from the ions. Okay. And if you heat up salt water on the stove, for instance, and you do that enough, all of the water will evaporate away, and eventually you'll be left just with salt residue on the bottom of the pan or whatever you use. Okay. But it doesn't. The salt doesn't have to be present. You just do that to water in general, and it'll evaporate away because all of the heat that you're adding to the pot is going to end up breaking all of those. You end up breaking all of those hydrogen bonds and individual water molecules and separate away. Now, it doesn't really take heat. You don't have to boil water to actually make water vapor. Because molecules, not just water molecules, but all molecules are moving around to some degree. And in the water, as a liquid form, that movement's always taking place, but it's not enough movement to separate the water molecules apart that they stop making these connections. So as I'm doing this in my hand, which you can't really see the models in my hand, but as I'm doing this, sort of the clicks that you're hearing are when the magnets come together and they stick. Liquid water does not have water molecules always stuck together like this. The hydrogen bonds are breaking and reforming all the time. It's just that the water molecules don't move away from each other enough to completely be separated, and so they reform to hydrogen bonds over and over again. And that lends to the coherence of water, and water molecules are stuck together by those hydrogen bonds. It remains as a liquid. It's when there's enough energy that they move quite fast away from each other, one molecule will be separated from the others, or another one like this, and you start to get water vapor as individual molecules are separated from each other. If we go the other direction and we cool water down enough, and I have to always keep one of these handy because it takes a long time to actually rebuild it. If I let the magnets do their job, eventually I get this kind of mishmash of water molecules. This is not what actually happens when you freeze water. This is what happens when you freeze water. The hydrogen bonds that are forming become more stable just because the water molecules aren't moving as much. They're probably moving a little bit, but not enough to really break those bonds. So as I kind of wiggle this one here, it's still stuck to the ones on the other side, it's just moving relatively, just a little bit. But those hydrogen bonds become more stable, and the water forms a crystal structure like this. This is an ice crystal, okay, an individual ice crystal. It's, of course, large enough for us to see and manipulate, but if it were at its real size, it would be probably almost beyond microscopic. It'd be really hard to even see a single crystal like this under a regular light microscope. Again, I'm not that familiar with the specific physics involved in all of this, but I do know that when ice crystallizes, it takes on this particular shape because this is sort of the easiest shape for it to take on. It's a six-sided kind of prism shape, which is to say that there's 6 water molecules on the top and 6 water molecules on the bottom, forming sort of a double layer of water molecules. And there's 6 faces around the outside of it. If you look at pictures of snowflakes, for instance, they're always going to have a 6-sided radial symmetry to them. The way that snowflakes form would actually be a crystal forms, and then another crystal forms, and they stick together. And then another crystal forms and sticks together. And it grows out in 6 directions from the center. They're always going to have that sort of symmetry to them. If you've ever made paper snowflakes, the traditional way of making is actually very wrong. You take a piece of paper, you fold it in half, and you fold it in half again, you start cutting shapes out. That would provide a 4-way radial symmetry. Just because of folding paper in half, that's the way it works. That's not actually what they look like. So if you have an art project that you're doing with kids and want it to be scientifically accurate, fold the paper up so that it's 6 pie-piece shape folds on top of each other. And I'm not going to go into how to do that, but that will be more scientifically accurate than your traditional kind of 4-sided, just folding it in half kind of thing. Now, it's hard for me to do this, what I'm about to describe, in just one hand without dropping water molecules all over the place. So pretend In this hand, I actually have the water molecules moving around like it's liquid water, so that the bonds are breaking and reforming and breaking and reforming. So this is a much more active group of water molecules than this one because it's so much colder. The movement that's present in these water molecules in ice crystal, they're just moving a little bit, but they're staying stuck to each other. What can you notice immediately that's different between these two groups of water molecules that I have here in my hand?
Formation.
Right. Much more regular formation in the ice crystal, because this is sort of the most stable configuration. This is not a stable configuration of liquid water, so it's a much more random grouping of water molecules. Can you notice anything else about this?
The density,
And what do you mean by that?
the one in your right hand,
Ice or water?
the water is more dense than the ice because there's spacing between the ice.
Right. So these two things are about the same size. Would you agree with that? Okay. There's actually two more water molecules in this one than this one. Okay. That's what you mean by dense. So density is just the amount of matter in a particular volume. So if these are basically the same volume, there's more water molecules in the liquid form that I have in this hand than in the ice or frozen form that I have in this hand. And you can see that very clearly in the ice crystal form. There's a big hole right through the middle. I could certainly take some more water molecules and cram those into the hole there and take up some space there. That's entirely possible. Maybe even a few more. Okay, so I've just crammed 5 more water molecules. I could probably get a 6th one up here on top. And that's practically the same volume. I've just squeezed more water into it, so it's more dense. Okay. Water, when it's liquid, is more dense than when it's solid, which is a very unusual thing, a very unexpected thing. Probably if I asked you, just stopped you randomly on the street and I said, what's more dense, a liquid or a solid, you're probably going to say solid, which is true for most every substance that you interact with on a regular basis. However, with water, it's not true. When water's solid, because of how it sets up this crystal lattice, it becomes, the molecules become spaced apart a little bit further, so there's empty space within this group of 12 molecules, and it's therefore less dense. What everyday evidence do you have to support the fact that solid water is less dense than liquid water?
Putting ice in a cup,
Yeah, because
ice floats.
ice floats. Less dense things are always going to float on top of more dense things. So anytime you put ice in a drink, you're proving over and over again that the solid water is less dense than liquid water because the ice floats. There's a video in the presentation that I posted. I think it was that video. I hope it was that video. What examples did they give regarding the difference in density between solid and liquid water?
You're not talking about the section where it had the water in the base, or is that too far?
No, it was a video.
Oh.
So it was just before what you're talking about, the picture of the book with the acid and base. A couple of frames before that, there was a video. I would hope that a video would really stand out for 2 reasons. One, it's moving on the screen while you're watching it. 2, it's not my voice.
It was a pond freezing with the ice on top.
Yeah, so when a body of water gets lower and lower in temperature, then this sort of thing's going to happen. It's going to crystallize like that. And the crystals, because they're less dense, are going to move to the top of the body of water. So in a pond, when it freezes, the top's going to freeze first. Now, the point of the video was to get at why water is important for life. And so it actually went beyond some things that apply to human anatomy and physiology. And so the example that we're using was how aquatic life fish, etc., that live in that pond can continue to live in that pond during the winter because the top freezes and the bottom still stays water because of the density difference there. So as far as these models go, that's about as much as I can demonstrate with them. So I want to talk about some other things with water. Again, what we're doing here today isn't exactly perfect for the recording like I do, but I am. So I've actually had, what you see with the projector here was the screen image that I froze there while you guys were looking at the water molecules. And so whatever poor sap's been watching this presentation has been staring at this page the whole time I've been talking here. But I was actually trying to find something else, but I couldn't locate it while you guys were working with the models. I'll see if I can pull it up a little bit, but I don't think it's going to work. Anyways, so I just talked about water. Let me come around because I am rather obsessive about this. I want to be sure I get the water molecules back from everybody. So.
Right here.
Thank you very much. So, what properties of water have we already demonstrated looking at this? So the properties of water. We've demonstrated, actually, trying to remember in the presentation, I had this little list of these. Did it say changes in density?
Changes in density.
Yeah.
Density.
I'm just asking what we've talked about so far. So changes in density.
High heat capacity.
That doesn't answer my question. So is there anything else that, looking at these models and talking about it just now, that we've already covered in the properties there? What else? I know there's at least one in that list that we also talked about, or I also mentioned. I remember saying the word.
The density based on temperature.
Well, that's what I got up here, but thank you for adding the temperature thing. Okay. But what else from that list came up when you were looking at it or I was talking about it?
Sodium. Sodium.
Is that in the list of the properties of water that were presented?
Cohesion and adhesion.
Right. What does that mean? Or which of those two words did I say? Or a form of one of those words? Okay, let's go back to.
Cohesion.
And what does that mean?
That means that they stick together.
Exactly. Why do they stick together?
Because the hydrogen bonds are always breaking and reattaching.
Right. So we were looking at hydrogen bonding and the fact that when the temperature's not too high, meaning it's not boiling away, water will stick to itself. That's cohesion. And then the other property, which I didn't say this explicitly when I was talking, I didn't say this word, but it goes with the same idea, which is water will stick to other things. And I demonstrated that with the sodium and chloride ions, that it was sticking to that. But it can stick to other things or larger things, you might think. In the video, when they were talking about that, does anybody remember, they didn't say it so expressly, but does anybody remember what the water molecules were actually sticking to besides themselves. And this example actually is very relevant to anatomy and physiology. So you remember what in the video was showing that might be anatomy and physiology related? It's obviously not a fish in a pond. What other kind of things did they show in that video?
The body.
What part of the body did they show?
Skin.
I don't think so, and that's definitely not the answer I'm looking for, but I don't remember there actually being anything about the skin demonstrated there.
Was it about blood?
Blood, right,
There you go.
because there's a lot of water in blood, so it's very important there. Does anybody remember what they were showing of blood, and how the water in blood can stick to other things? So that was actually in the video where they're talking about cohesion and adhesion. So they're showing that the water molecules in blood plasma are attracted to each other because of hydrogen bonding. But then also, and you might not remember this from the video, but hopefully you can kind of make the leap to understand where I'm going with this. What would the water molecules in blood plasma be attaching to, adhering to?
Not cells.
Yes, cells. That's a fair answer to what I'm asking. But let's see if we can figure out which cells specifically it would have been attached to. And I'll give you a hint, it's not the blood cells.
Not white.
So if your blood, besides blood cells, what are you going to come into contact with?
I'm just gonna say.
If you start to say plasma, you are the plasma, and I'm asking what do you come in contact with besides the blood cells?
Oh.
Where do you find blood?
Veins.
Veins and arteries. Collectively we call them. Not that broadly. Yes, that would be true. But collectively, veins and arteries are two types of what particular structure?
Oh,
So that's the system they belong to.
oh, freak. What is it?
What does it start with?
Actually, it's two words. The first one's blood. The second one starts with a G.
Vessels.
Vessel. Right?
Oh.
Blood vessel. So as far as the cells that I'm talking about, besides the blood cells that the plasma interacts with, it's also going to interact with the cells that make up the blood vessel walls. And in fact, in the video, there's this sequence where they have this blood vessel and they have water in there and red blood cells. And they show that it's the water molecules are attracted by hydrogen bonds to components of the blood vessel walls. What it is that there are going to be proteins and carbohydrate molecules attached on the outside surface of cells, and so as water goes past them, it will interact with that. And that was actually sort of what the video was showing. They didn't show it, they didn't state it quite as explicitly as what I'm saying here, but that's what I was getting at. One thing I thought was kind of funny from where they did that is they had the blood vessel and they labeled a couple of things like water molecule and red blood cell, and they might have pointed at the vessel wall or something like that. Under red blood cell, it said not to scale, okay, which is true. But what was really funny is the water molecule, if it was depicted as about this size in that video, the red blood cell was depicted as about that size. And so they're saying, well, that's not to scale. But that was more to scale for the picture, considering the blood vessel walls where they were drawn, than the water molecule was. But they really should have said is the water molecule is not to scale. I just found that kind of because scale is important. Okay, when we get to talking about cells and those sorts of things, it's made up of water molecules or larger molecules like proteins and lipids and that sort of thing. The number of water molecules that are present inside of a cell or in the solution like plasma surrounding cells is immense. There's billions and billions and trillions of water molecules there. They're just everywhere. They're ubiquitous. And it's important for us to think about them because they're so important to what's going on in our bodies. The simplest life exists in oceans, in a water environment. And life, as it became more independent and moved out of the sea, was able to do that because it was able to keep a liquid environment inside. So what's going on in our bodies chemically is very similar to what would go on in the sea. It's just that it's contained within our skin, and then there's various smaller compartments inside. We get down to cells, have their own little water inside of them, that sort of thing. But water's everywhere. There's a lot of it. Okay. Those are the major properties that we really could touch on with the models I just showed you. So let's move on to other properties that were provided there. What's another property that was presented in the video, and I wrote down in the presentation right after it? Somebody give me one of them.
Universal solvent.
Okay. So universal solvent. Now, this is an important point, which actually kind of comes off of what I was just saying there. Although, really, if you're going to say this, and nobody ever does what I'm about to say, but really you ought to put a little asterisk next to it. What is solvent?
The substance that's going to be dissolved.
No, it's the exact opposite
Or
of that.
sign is the
Yes, solute's what's going to be dissolved, so solvent is
liquid.
what it's dissolved in. Okay. It's the medium that you can dissolve. So a universal solvent would mean what everything could dissolve in. Okay. And I put an asterisk there because really there's no such thing as an actual universal solvent. Okay. If there were a universal solvent, you wouldn't be able to contain it in any kind of container. Okay. Imagine if plastic could dissolve in water. You couldn't put a water solution in a plastic bottle because it would dissolve the bottle, okay? Or glass or whatever. So a true universal solvent is a fiction. There's no such thing as actually a universal solvent. But water is a very good solvent for a lot of things, but it will only dissolve things that satisfy a particular let's call it a rule. Okay. What sorts of things dissolve in water?
Salt, sugar.
Okay, so by salt, I'll assume you mean table salt, sodium chloride. By sugar, I'll assume you mean glucose, which would be C6H12O6. What are the kind of things? Oh, and I'm assuming these just because they're what we usually think of, but there are other salts and there are other sugars which also dissolve, but I'm using these as examples. What are the kind of things dissolve in water?
Powder? Energy?
What's the powder made of?
I don't know.
Give me an example of a powder that dissolves in water.
Like, you make like an iced tea.
Okay. I was hoping you'd go for Kool-Aid, but yeah, so what is that made of? So there's going to be some sugar in it. What else is going to be in there? So there may be other carbohydrates that aren't specifically sugar. Sugar is a carbohydrate, but you're correct. where does tea come from? What is tea?
Leaves.
Leaves, which means that they are plants. Um, and for plants, leaves are the green part usually that actually do the photosynthesis reactions. Which means that they make carbohydrates from energy and water and carbon dioxide. So there's going to be carbohydrates, all sorts, plus including sugars like glucose, but other things, dietary fiber and that kind of stuff is going to be in there. And then there's going to be a whole host of other molecules that give it its particular flavor. Okay, and I don't know precisely what molecules are all involved in flavoring iced tea or Kool-Aid for that matter. But anyways, yeah. So those are kind of things that dissolve. And essentially everything in here ultimately comes from a plant like a tea. What other kind of things dissolve in water?
Food color? It doesn't dissolve, but it.
No, it's fair to say it dissolves. You're probably saying it doesn't dissolve because you're starting off with a liquid and adding it to a liquid. But that's still dissolving. It doesn't have to be a dry solid that gets incorporated in. That's just what we usually think of as dissolving. But yeah, it'd be that.
Also, now dry food coloring, that's what they use to make like fried Easter eggs.
Right. So like if you get an Easter egg coloring thing, instead of liquid food coloring, it's probably the exact same thing, but it's in a little pellet, which is easier to sell and transport, that sort of thing. So I'm just going to put dye here just to add to this list. Yeah.
I have a question, like, what about like, what are bath beads made out of? You know how you can put bath beads in
Oh,
water
bath
and
beads.
they dissolve?
That's an interesting point to make.
Just curious.
No, it's a good thing. It's going to have detergents in it, not necessarily soap like what you're going to use, ivory soap kind of detergents, but belonging to that same class, which will help dissolve things that shouldn't dissolve in water. Okay, so I'm kind of painting myself into a corner here. So we're going to try to get out of it, and we're going to use the bath beads to do that. So what kind of things don't dissolve in water?
Oil.
Fat, oil, they belong in the same thing. So in the bath beads, the reason you're using them is because you're going to be introducing lipids, which is what we call the group that includes fats, to the water to make the water, softer, if you can use that term. But lipids won't dissolve, so the detergents that are mixed in with it make it possible for those fats to dissolve. Okay. If you want, the reason why I'm using the word detergent, you can probably imagine this if you've ever seen a Dawn commercial. They always make this point about how Dawn gets the grease off or whatever. Detergents are essentially detergents because they can help make lipids soluble in water. Okay. They don't do anything necessarily to the lipid, they just coat it in molecules that make it the whole thing dissolve in water, which are the detergents. So what is it about lipids that they won't dissolve? What is it about lipids that makes it impossible for them to dissolve in water unless they're treated with a detergent like that?
Fatty acids.
Which is just another word for lipids. So what is it about the lipid or the fatty acid that makes it not dissolve in water?
Are their bonds too strong?
They're
Are their bonds too strong?
they're not too strong, but it is about the bonds. The bonds that you'd find in a lipid or a water molecule or a sugar molecule, the same strength bonds, but there's a categorical difference between them.
Their valence shell is full.
No, every valence shell should be full in a stably bonded compound. But if you think about the types of bonds, the strong ones are the covalent bonds. Okay, that's everything we were talking about here is covalent and bonded. but there are two types of covalent bonds. What are they?
Polar and non-polar.
Which one is found in substances that dissolve in water? Polar, right. Why? Because water's polar, exactly. Okay. So if we're over here and we're looking at a water molecule and it has a partial positive and partial negative charge. Okay, do the whole thing here. It's making hydrogen bonds because of that polarity, and it's able to be attracted to other things that are also polar. So charged particles like chloride or sodium, or larger molecules that have charges associated with them, which would be true of C6H12O6. And then the components in powdered tea or dye, those are all polar substances. The molecules in them have some charged aspect to them, whether it's a very charged aspect, like it has a positive or a negative charge, like sodium or chloride, or it has a partial charge, like we see across the water molecule here. That's still making it polar. I'm going to see if I can pull something up on the screen real quick that'll go with this. Actually, no, I know what I can do. It'd be quickest for me to just go into the book. Oh, that's interesting. Since I have this up on the screen, I'll just mention it, just a little thing. If you ever open up a link to the book and it has a yellow bar up at the top that says newer version, click that. That means that they've updated something in the book, made some sort of correction somewhere. And when I see those, I will try to update the link in the book. So yeah, always, if it says there's a newer version of the book, go to it. Just because that means that there's some error, typo, whatever they fixed along the lines, along the. It's better, just do it. Where was I? Oh, introduction, chemical. So I had this particular table as one of the pictures in the presentation because I want to talk about this. And this is getting at functional groups. Can anybody remember how I defined or described functional groups in that presentation? Nope. Right. They are, they're not molecules to themselves. They're parts of molecules. But they're specific groups of atoms that are bound to each other in a particular way. That when they are bound to, or when they are part of a molecule, when they're bound to more stuff, they give the rest of the molecule particular properties. The hydroxyl group is an oxygen bound to a hydrogen, which is essentially 2/3 of a water molecule. So this is a polar bond exactly the way that the hydrogen-oxygen bond to water is polar. It's kind of like that molecule has a little bit of water as part of it. It's essentially the same property. It's the same polar property as you'd expect with water. Carboxyl is the way that they chose to type these into the table, there's a little thing that's a little kind of messed up here, but that's okay. It's a carbon that's double bonded to an oxygen. So this line here really should be a double line, but the way that they made this table, it doesn't come across that way. And then it's bound to an oxygen-hydrogen, which is essentially a hydroxyl. Any molecule that has a carboxyl group in it is considered an acid, an organic acid. So amino acids, nucleic acids, fatty acids, they all have one of these in them. Okay. It's not the only thing that makes something an acid, but when we have an organic molecule that we refer to as an acid, it probably has one of these in it. This is an amino group. The name is very similar to the word ammonia, which is where it comes from. Ammonia is NH3. So this is NH2 as I depicted here, and the third hydrogen has been taken off because this would be attached to something else. And I'm going to jump over the methyl group for a second and point out the phosphate group, which is phosphorus with a number of oxygens attached to it. The reason I'm skipping the methyl for a second is because of this list, these functional groups that are common in the types of molecules we're going to deal with, except for methyl, all of these have polar properties to them. Hydroxyl, carboxyl, and amino all have polar bonds in them. Phosphate has essentially polar bonds in it too, but the number of bonds that are made are such that there's 2 negative charges present in them. And let me just depict that a little bit. So this is how we draw a water molecule, usually. If I do the same thing to draw a phosphate group, it would be like this. So the line that doesn't have anything attached to it, that would be what's part of the bigger molecule. And so all of this is stuck out here. Oh, I should do this one differently, like that. Now, when I'm talking about bonds in the presentation, what did I tell you about the number of bonds that certain things can make? That's a little quick bit of information that you should have on hand all the time. It's important to keep that in mind.
There's a question again, I'm sorry.
What information in the presentation dealt with the number of bonds that things can make?
It was the hunk thing, right?
Right. Yeah. So HONC, hydrogen, oxygen, nitrogen,
Oxygen is
carbon.
2, carbon 4, nitrogen 1, nitrogen 3.
That's a very weird way to.
I just did it in order and then I spelled out hunk afterwards, because that's
Well,
what
you
the
should
order
spell
was
honk
in.
first, and then the point of honk is that it then gives hydrogen 1, oxygen 2, nitrogen 3, carbon 12.
That was the order it was
Right.
in.
The order that you're talking about is, I think, based on how much is present in the body, which is fine. I don't really care about that order too much. We're not going to sit around and say, okay, is there more oxygen or more hydrogen in the body? Mostly because that is either not that important because they're parts of other things, or it's self-evident because there's just so much more oxygen in the body. So in the honk thing, the numbers that I'm talking about here, so I'm not saying you're wrong what you're saying,
Yeah,
just
I figured.
saying it that way just struck me as sounding very strange. Rearrange them. Anyways, so from that information, what about what I've drawn up here just seems plain wrong?
Two double bonds,
Well,
or the double bond.
there's one double bond, but that's actually the thing that shouldn't be valued. It's the other 2 bonds that should value because they're not double bonds. Okay? Oxygen makes 2 bonds. Okay? But as I've drawn this, these oxygens are represented with just a single bond each. Okay? So they're not happy. Okay? And because of that, they're going to each have a negative charge. Not a partial negative charge, but they are going to have a full negative charge. One more electron than proton. Okay. And then this one over here is all happy because it's got 8 electrons in its valence shell. It's good. But these two are off. Now, actually, the way that I've drawn this is a little bit of a simplification. Phosphorus can make 5 bonds. Not quite the same way that I'm talking about here, but it makes 5 bonds. And when it makes bonds with oxygens and whatever it's connected back to, it distributes the bonds across the oxygens equally. This is really weird chemistry. And don't worry about it, but I'm just trying to make a point. That really what it is like there's a third of a second bond there, and a third of a second bond there, and a third of a second bond there. And so in the end, there's a -2 charge to the whole thing. Okay. Chemistry can do this. I don't want to get into what, but that's what's going on. So hydroxyl, carboxyl, and amino have partial charges in them because of the polar bonds between oxygen and hydrogen, carbon and oxygen, or nitrogen and hydrogen. The bonds between phosphorus and oxygen are more than polar. They result in negative charges to considering all the players involved. It's a -2 charge. Okay. And I just noticed a little. I think they have an error in that, but I'm not positive. I don't know. As far as the numbers, but don't worry about that. It is a -2 charge. So any molecule that has those things in it is going to be able to interact with water to some degree. A fatty acid has a carboxyl group in it, but not all fatty acids dissolve in water. The carboxyl end of a fatty acid will dissolve in water, but if it's a very long fatty acid chain, it as a whole will not dissolve in water. Which brings us to the methyl, which is the one thing that doesn't dissolve in water here. And essentially a fatty acid chain is just a chain of methyl groups, okay? Just repeating carbons over and over again. Why is the methyl group different from the other ones here? What have we been talking about? Let's do the bonds that I've been talking about. Are these bonds different from all the rest of the ones here? So I asked you to recall for me essentially the honk information. In the presentation, sorry?
Carbon should have 3 bonds.
It does. No, well, it got 4. There's one there, and then this says H3, so the other 3 are there. So the number of bonds is fine. But in the number of bonds information I just had you recall, there was the honk thing. Right next to that in the presentation, there's another little bit of simple. Commit these things to memory, and it'll be easier for you. What was the other thing I tested there?
The polar and non-polar bonds?
Right. So that's your clue. What's different between methyl and all the other things?
It's non-polar.
Yeah, these are necessarily non-polar bonds. The electronegativity of carbon and hydrogen are so close together that when they make a bond, they share the electrons equally, as opposed to, erasing. But in the water molecule, the electrons are around oxygen more than hydrogen. Okay. It's not the hydrogen that makes it a polar or a non-polar bond. It's how hydrogen compares to whatever's bonding there. And hydrogen and carbon have very similar electronegativities, so that's a non-polar bond, whereas when it bonds with nitrogen or it bonds with hydrogen, it's polar. Okay. And when oxygen bonds with carbon, or it's not in the list I gave you, but when phosphorus bonds with oxygen. Those set up, I have to take back that thing I just said about phosphorus, because I really don't understand the chemistry in that as well. But for the big ones that we're worried about, carbon, let me do that correctly, hydrogen, oxygen, nitrogen, and carbon. For those four, when hydrogen is bound to carbon, it makes a nonpolar bond. When hydrogen is bound to either of the other two, it makes a polar bond. What else? Well, okay. So methyl's different from the rest because it makes polar bonds. A methyl chain, like a fatty acid chain, is essentially what lipids are based on. So lipids don't dissolve in water because they are all made of non-polar bonds, whereas all of these other things fall into what we would consider polar, and they do dissolve in water. So what I was trying to get to, starting this list, which I really was ill-advised of me, was to get to the idea that it's a universal solvent for polar substances. Non-polar substances will not dissolve in water. And so that plastic bottle doesn't dissolve into the water that it contains because plastic is a non-polar substance. Plastic is essentially a synthetic lipid. Okay. It's mostly hydrocarbons, but it's synthetic. So, there's no such thing as like a plastic plant that you can get plastic from, but you can make it out of hydrocarbons, that you get in petroleum products like oil and that. But that's a sidebar. Okay, what other properties of water were given in the presentation? Okay. That was actually a separate?
Yeah.
Okay.
High surface.
Sorry?
It was high surface tension.
Oh, that's right. There were two high ones. Now, high surface tension is really just a matter of cohesion. Okay, so I'm going to deal with this really quickly, which is good because I'm trying to wrap things up in a couple of minutes. Cohesion is just water molecules sticking to each other. When you get to the top of a water solution, where it's sort of interfacing with air or something like that, the water molecules at the surface are going to be attracted to each other, well, as much as they should be anywhere in there, but at the surface, the cohesion becomes a bit more, I don't want to say organized or anything like that. It's not like they crystallize, but it becomes a little bit better so that there's some tension at the top. And so in the video, they had like a water walker kind of bug they represented there. It takes a little bit to push through the surface of the water. And so something that's very light, like the legs of an insect, won't push through it. Okay. As far as how that's really important for what we're going to be dealing with in this class, it's really just how it's a matter of cohesion. Okay. And the only place that it really comes up is in the respiratory system, which is an AMP2 thing, so we're not going to really talk about that this semester. So there was a fifth thing. What was the fifth thing on the list? It's another high something. We got that one.
High heat capacity.
Yeah. High heat capacity. Oops. Now, heat capacity just describes how well a substance can absorb heat. Okay. That's sort of why the word capacity is used. But really what it's talking about is how much energy it takes to change the temperature of something. So with water, it takes a lot of energy. Quantifying that is a little bit misleading because water, being so important to everything, is the basis for most things. So the heat capacity of water is often described as the amount of energy it takes 1 milliliter of water to increase its temperature by 1 degree Celsius. Okay, so all of that's one unit of whatever. Wait, is that right? I think that's right. Because all of those ideas are based on what happens to water. Things with lower heat capacity, the same volume of whatever it is, takes much less energy to change its temperature by 1 degree. Okay. Water has a very high heat capacity. That's important for life in general because having water in the oceans underneath the sunlight all day long does not evaporate all that water. All of the energy and sunlight that's hitting the oceans, it can evaporate the water somewhat, but not enough to make the seas disappear. So the seas stay where they are for the most part. A little bit evaporates away, which eventually will fall back down in the form of rain later on. But the big sea that all of the aquatic life lives in stays put, so they aren't like on dry land overnight. Inside our bodies, that's important because our body temperature is really a matter of the temperature of our blood. And it's really hard to change the temperature of our blood or bodies, however you want to think about it, because of this high heat capacity. And it makes it possible for our bodies to keep a very constant temperature. Okay, you can walk outside on a hot day and your body temperature will remain fairly constant because it takes a lot of work to change the temperature of water. And we also make use of that through sweating to radiate off as much heat in making sweat evaporate. So I just want to touch on those things to stress the properties of water thing today. Next time on Thursday, I'm actually going to kind of pick up with the functional groups a little bit and lead into talking about the macromolecules. I'm going to concentrate on proteins and kind of like with the water molecule models that we dealt with, I have protein model stuff that I'm going to have you deal with to get to understand proteins a little bit better. So we'll do that on Thursday. And then next Monday, we're going to start looking at things under the microscope and start talking about cells. So I think that's everything. Thanks for holding on for a minute or two. And I'll see everybody on Thursday.